Okay. Good afternoon, good morning, everyone, depends where you are. So today we are happy to continue our Frank Wilczek's lectures on the thermal symmetry in physics. So I'm Qing Dongjiang from Central East. So the symmetry has a very simple physical intuition, but have very far-reaching physical consequences. So, most people here probably know Zhiyuan Yang. So Zhiyuan Yang, in his Nobel lectures, explicitly say these following words: that if one pauses to if Zhiyuan Yang in his Nobel lecture said that if one pauses to think the elegance and the beautiful concept of the symmetry principles and compare it with its far-reaching and complex physical consequences, so one always has a deep admire on the symmetry principles in physics. So actually, symmetry principles is more than physics in any other areas. And among all the symmetry principles, thermal symmetry is very special. As in special relativity, it has a different signature. So thermal symmetry is special, and Frank is also special. So let's welcome him to give a lecture. Okay, continue. Thank you.
Let me get a time reversal entrance. Well, thank you for that introduction. Thank you for coming on this beautiful day. And here we go. we're kind of in the middle. Let me recall for you where we left off. So we proved at the classical level, following Kobayashi and Maskawa's ideas, that the very restricted appearance of time reversal in the world could be understood within the standard model, within, in other words, the principles of quantum theory, relativity, and the gauge symmetries of the world, and the particles that actually exist that represent the symmetries, that we could almost solve the riddle of why the laws of physics are almost, but not exactly, invariant under this transformation of time reversal. But then we found a loophole, or an exception to this wonderful picture. That is that there's another possible interaction that they didn't consider, that is more subtle, that involves us in the depths of quantum field theory and topology, and introduces another term whose coefficient is theta, is usually an angle that parametrizes the strength of interaction among gluons, color gluons of QCD, of the form E dot B, but now in the color fields instead of the electromagnetic fields. And it's odd under time reversal. This parameter theta is odd under time reversal, as E dot B is. So T symmetry holds in only two cases, two particular values of this parameter, for theta equals 0 or pi modulo 2 pi, which is its physical periodicity. And so there's a second consistent T-violating parameter different from the one considered by Kobayashi and Maskawa. So their explanation, while a big step in the right direction and very fruitful, is not quite complete. And it was easy to overlook this interaction theoretically because phenomenologically it's not necessary superficially in describing the world. In fact, people have looked very hard for one of the main effects that would cause an electric dipole moment of the neutron. And the experimental limits on that quantity, which can be measured very, very precisely, and people have worked for decades gradually improving the limits, they translate into a constraint on the value of this parameter, which would be expected to be of order 1 in the absence of any special principle, is in fact less than a part in 10 billion. So that's pretty striking and is a challenge for theoretical physics. We would like to have a qualitative understanding of such a remarkable coincidence, or remarkably small value of a parameter in the world. So the bottom line of our T-violation story so far is that we've come a long way towards tracking the observed pattern of T-symmetry violation to deeper principles, but our work's not quite done. Okay, so in bringing us to that point, which was an important milestone in these lectures, I kind of surveyed but did not give details of the underlying argument. And this lecture will be largely filling in the discussion that leads to that conclusion. And in fact, and I'll bring in also connect other topics in physics that are very interesting that are logically connected to this main goal. So we're doing the hard theory of chiral anomalies. And this is another long story, and one of the glories of theoretical physics, actually, this story, and it's still ongoing. People have been finding more and more applications of the reasoning that I'm going to show you. But let's go back to the origin story. It was a very concrete problem in the description of the strong interactions, and well, in the description of the pi-zero meson, a very particular thing. When people measured the pi-zero lifetime, which is dominated by the decay into 2 photons, there was a discrepancy between theory and experiment. The theoretical prediction was too small. There's a symmetry, an approximate symmetry of the strong interaction that predicted that if that symmetry were exact, I'll fill in details momentarily, then the result would be 0. And it wasn't 0, it wasn't even particularly small. So this failure motivated people to look at the assumptions of the theoretical calculation more carefully. And that revealed a big surprise, which has sort of caused a continuing earthquake in physics, in quantum physics. That is that when you quantize a classical theory, you can find that the quantum theory necessarily has less symmetry than the classical theory. You lose some of the symmetries of the classical theory. Symmetries that are spoiled are called anomalous symmetries, and the symmetry breaking terms are called. There are several different types of anomalies that play a role in different parts of physics. I'll mention just one besides our main topic, the chiral anomaly. One anomaly that's very, very important is the scaling anomaly. If you take QCD with 0 quark masses, which is a very good approximation for the quarks that make up nuclear matter, the up and down quarks, they weigh much, much less than a proton, for instance. Then the theory has no dimensional parameters. which the classical theory has no dimensional parameters, which is another way of saying that it's scale invariant. You can change the measure of length or the measure of mass, and the theory stays the same. Its only parameter is dimensionless. That would be a disaster if the theory is supposed to describe the world, because the strong interaction particles do have a definite mass. And also at a more mundane level, there are experiments, especially the experiments done at the Stanford Linear Collider in the 1960s and late 1960s that indicated that the interactions have scaling violations, and that was the problem that I studied in my thesis that led to QCD and modern QCD and asymptotic freedom and so forth. So that was the fact that interactions, the quantization of the theory, necessarily spoils the scale invariance. So another symmetry that's spoiled is the separation that we observed between left-handed and right-handed propagation of massless fermions in free space and also in their interaction with gauge fields. So that's a chiral symmetry. The fact or the idea, the transformation that you can make separate unitary transformations on the left-handed and right-handed components of a field is the chiral symmetry. Okay, and we discussed in very concrete detail the classical Lagrangian on which the standard model is based, and it did have this separation of left and right, messed up eventually by the Higgs field getting a vacuum expectation value, but for many purposes that can be neglected when we're dealing with very light fermions, and in the basic formulation of the theory where the masses were zero. So if we can just consider free propagation of fermions or their interaction with gauge fields, they don't change the chirality. They leave left-handed particles left-handed and right-handed particles right-handed. That means that we have, in addition to the conservation of the number of particles, we have number of left minus number of right conserved. And in terms of currents, we have a conserved current that reflects the conservation law. And we have then also a conserved current for the axial part, left minus right. And you remember left was 1 minus gamma 5 over 2, right was 1 plus gamma 5 over 2. So the axial current is just gamma mu gamma 5. So that's the formula that reflects conservation of the axial current. Okay. But, and this is the calculation that I referred to of that was motivated by pi 0 to 2 photon decays. If you calculate the divergence of the axial current associated with some massless fermion. Now, I won't trace back, but in the theory of QCD, or at the time this calculation was made, it was not really QCD. There was a certain amount of guesswork, but in theoretical framework that people use to discuss pi 0 decays, you represented the pi 0 field as divergence of this axial current. So that has the right quantum numbers to be a pseudoscalar. It's actually the fermions are the up quarks minus the down quarks in modern language. And you just go ahead and calculate this Feynman graph that, and we can think of this, let's forget the background of pi 0 goes to 2 gamma and just, for our purposes, skip to the chase, you find instead of a 0 result, which the conservation law would say when you do this calculation, you find a non-zero result. You find that you get a contribution to the Lagrangian, which is proportional to E dot B. Okay, it's this thing that keeps occurring. It would be the theta term in QCD. Here, it's appearing in electromagnetism. This happens in a very, very interesting and subtle way. That's why people had to sort of have their nose rubbed into it by experiment to recognize it. Okay, so when you do this calculation naively, okay, those of you who know about Feynman graphs, you'll appreciate this. If not, well, look it up, and I hope this motivates you to go a little bit deeper. So this is the setup. We have the momentum of the current going in here, and then we have the momentum of the photons, K1 and K2, and we have the interaction vertex of the current here. So we're going to calculate the matrix element, or the P mu dotted into gamma mu gamma 5. Like that, using the interactions that photons have. And we have here 3 fermion propagators. Whoops. Each of which at large virtual momenta, so we have a virtual momentum flowing through the graph, each of which goes like 1 over the momentum. And then we have to integrate over the 4 vector of momentum flow. So our integral looks like this at large values of Q. I don't know what happened. Something happened.
The internet is not so stable.
Okay. The internet objected to these infinities, I guess. I'm being very schematic. I just want to show the why it's divergent.
The action will come from the spin sum, so that you take a trace.
Yeah, you take it when you do the Feynman graph in more detail. Here, I just want to show you that it's a delicate Feynman graph. It's infinite unless you treat it carefully. Well, it's just plain infinite at this point, and so that's a sign you have to treat it carefully. Okay, so you have this virtual momentum grows, and then it's only compensated by a 1 over Q cubed, so the total integral diverges. This is the ultraviolet divergence, which I commented earlier is kind of the new quantum mechanical version of the black body radiation catastrophe that started off quantum theory. Okay, we don't have problems with thermal fluctuations, thanks to Planck's hypothesis and the development of quantum theory, but we have new potential sources of spontaneous fluctuations, not thermal, just quantum fluctuations that are very dangerous at high frequency. So the attitude to physicists at the time, before the experiments, or physicists who didn't worry too much about the underlying theory, was that we could sweep this infinity under the rug because we know the symmetry has to be true. So somehow there have to be cancellations, and you get infinity minus infinity is 0. Now that sounds kind of fishy, but people still make that kind of argument all the time, like in the case of the so-called cosmological term or dark energy. You can calculate naively, many contributions that are infinite, and people say, okay, well, somehow they've got to organize themselves into a finite answer, which in fact is very small, very, very small. Okay. However, in this case, we can hold ourselves to a higher standard. Before claiming any cancellations, we can make sure our integrals are finite by a so-called regulation procedure, and then try to take away the regulation. Okay. So I'll show you exactly what that means in this context now. So we want to introduce some parameter that, crudely speaking, cuts off the dangerous, very high momentum virtual modes. Now, but we want to do this in such a way, and then we'll relax the cutoff and see if we can get a finite, legitimate answer as we take the cutoff all the way to infinity. But at intermediate stages, we want to have finite things that make sense. Okay, so in doing that, we want to maintain gauge invariance of the theory for many reasons. I mean, gauge invariance is a key part of the standard model, and also not only conceptually, but as part of its mathematical consistency. And in this context, it's especially good because gauge invariance, if we do manage way of regulating these integrals was invented by Pauli and Villars. And it is to introduce a very massive spin 1/2 boson, B, with exactly the same quantum numbers as our fermion F that's appearing in the integral, in the physical process. Okay. That violates a famous principle of quantum field theory called the spin statistics theorem. And we're not going to take the time to prove the spin statistics theorem and to show why this is a thing you really can't do if the boson had finite mass, but we're going to take the mass to infinity. And so the boson will not actually be producible in any physical process. Okay. But in terms of Feynman graphs, bosons and fermions contribute with a minus sign, a relative minus sign. That's related to quantum statistics and anyons, if you look at world lines in space-time. That's for another discussion. So it comes into the loop with the opposite sign, and therefore, at high momenta, where we can ignore the mass, it really will cancel and be finite. Okay, so it's this tricky thing. We introduce the mass, then the integrals are finite, but then, and only then, do we take the mass to infinity. So we regulate and then take the mass to infinity. So we don't, because we don't want this particle. Okay. And then, now, this fictitious boson, this Pauli-Villars regulator boson, is massive. So it does not have chiral symmetry. Mass terms, you remember, connect left to right. And in fact, you can easily calculate, if you're familiar with the Dirac equation, that the divergence of the axial current is proportional to the mass. And so, now, assuming that we have gauge invariance, because we haven't done anything that violates gauge invariance here, and so we'll have that structure I mentioned with a K1, K2, and like that. It'll be finite at large values of momentum, but this M will appear outside. And so as M goes to infinity, this whole thing approaches a finite answer. Okay, the integral only converges like 1 over M and cancels this M. So we get a finite answer as M goes to infinity. So it's sort of like the Cheshire Cat. This boson goes away in all physical processes, having done its job of regulating the integrals, but it leaves a smile behind, which is the fact that the current is not conserved. The total current, including both the fermion we started with and this Pauli-Villars thing we needed to introduce in order to make it behave properly at high momentum. So that's the anomaly. We had a symmetry, but necessarily when we introduced the fluctuations that quantum mechanics requires, which is represented by these virtual particles moving around, the symmetry cannot be maintained. Now, it turns out, this sounds miraculous, but we'll sort of prove it, is that this simple triangle graph supplies the whole answer. And then, going back to the original history, once that insight is applied to the pi 0 goes to 2 gamma analysis, the theory does match the experiment. So, okay. So that's the history, and I think sort of introduces some of the key ideas. Now we're going to look at them more mathematically and rigorously. And in this part of the lectures, I will have to assume a higher level of sophistication than elsewhere. I hope if you haven't seen these things before, I hope you look them up and this inspires you to deepen your knowledge of the relevant parts of quantum theory and quantum field theory. Okay. I recommend, if you want to read a book, there's a book by Anthony Z called Quantum Field Theory in a Nutshell, which has a very good discussion of this. There are also some recent lecture notes by Hans Hansen and a couple of collaborators, and I will supply a link to that so you can look at that as well. Okay, so was there a question? Was there a question?
Well, my question is really naive. Is that you just calculated a loop diagram?
Yes.
With the fermion loop, then why does it lead to a change in the Lagrangian? Where you say that where you say that delta L is proportional to something called theta.
Well, any interaction is a contribution. Any interaction that you find is a contribution to the Lagrangian. Not to the primary Lagrangian that we use to formulate the theory, but to the effective Lagrangian.
Okay, so that part is simply effective. It's not.
What's that?
So you mean that part is simply effective?
Yes.
Okay,
it's a result. I mean, it's just another way of stating the result of the Feynman graph calculation.
Okay, thank you very much.
Good question. Okay, so when we deal with quantum mechanics in the Feynman path integral formulation, where we integrate over all configurations of things that might have happened, when we have classical fields, like the electromagnetic field or a scalar field, it's pretty clear what to do. There are subtleties about integration in function space, which is an enormous space, but at least we know that we're integrating over numbers. The classical fields are numbers. When it comes to fermions, it's different. It turns out, and I won't go, it would take another separate lecture to really justify this, that when you want to calculate the basic quantities of a quantum field theory, for instance, its partition function, which if you calculate the partition function in the presence of sources, you can basically calculate everything, that what you have to integrate over for fermion fields are numbers that satisfy x times y equals minus y times x. Those are called Grassmann variables. Okay. So you won't find them in respectable mathematics books, but that's what physicists deal with. And so the central result that emerges from using Grassmann variables is this, that if you integrate an exponential of some operator, so it might be, the operator might be a derivative or derivative and multiplication by functions, things like that, involving the gauge fields. So the things that are kind of things that appear in our standard model Lagrangian, that general sort, what you get is the determinant of that operator. So that's the central result of defining quantum field theories involving fermions using the path integral. So I'm going to use that, but only a little bit. So if you're willing to bear with me, take that as given, you won't miss too much. Okay, so now we want to implement Noether's theorem, or see how Noether's theorem emerges, that links symmetry to conservation laws in this particular case. So the symmetry transformation is a transformation that gives opposite phases to left and right-handed fermions. That phase transformation is conjugate to number conservation. So phase transformation is conjugate to number. It should be familiar in the case of electric charge. And if we make this kind of transformation on the Dirac equation, on the Dirac Lagrangian, psi bar del mu psi, with or without gauge fields, you find that L transforms only because of the derivative of alpha. If alpha was a number, we'd have the regular transformation of conjugate to number. So the only thing that survives when you make this transformation is the gradient of d mu alpha, like that. And you could also see that directly by calculation. Okay, so the statement that the theory is invariant under this transformation is the statement that the integral of the thing that appears in the partition function, e to the I action, doesn't change, and that is equivalent to the fact that when you take this change in the Lagrangian and insert it into that expression, it gives 0. So the x of this current is conserved. Still massless fermions, yes. It's all massless fermions. Right. Okay. However, that integration over the fields is an integration, as I mentioned, over a gigantic function space. And when you make a transformation on an integral like this, you not only have to transform the integrand, you also have to transform the measure. There's a Jacobian when you make a transformation on an integral. Now, the intuition was that integrating over all functions somehow doesn't introduce any subtleties in measure, but that's not true. The essence of the anomaly is you really have to pay attention to how you're defining the measure. Okay, so we're calculating the Jacobian, which is the determinant of this transformation we've made in function space. Okay, now the determinant is the exponential of the trace in general. So what we need to calculate in order to do the full transformation that implements the logic of Noether's theorem, this connection between symmetry and conservation laws in the context of quantum field theory, is we need to evaluate this trace in function space. Okay. And here, for simplicity, let's suppose alpha is a numerical constant, so we don't have to worry about. Well, actually, it doesn't even matter. But now, in the next few minutes, I'm going to evaluate this in two ways, two very different ways. The fact that the evaluation is evaluating the same thing means that the two things will be equal. They will, however, be far from obvious that it's equal. And the fact that they are equal was discovered in mathematics as well as physics. In physics, it's the anomaly equation. In mathematics, it's the Atiyah-Singer index theorem. Okay. Now, I'm going to do this proof in approximately 10 minutes, which means that some details will be omitted. But as I said, I hope this motivates you to look at more fully fleshed out presentations. Okay, so the first evaluation is, okay, we have a determinant of an operator. Let's look at the eigenstates of that operator and just do the determinant. Multiplying. So we actually look at the eigenstates of the Dirac operator, this thing. Okay, because that's a good thing to do, because now what we're actually interested in is the trace of gamma 5, as you saw, but those are related here. Because that's the right-hand side. And now you see that we have the eigenvalues coming in pairs with lambda and minus lambda. When we multiply a solution that has lambda by gamma 5, we get a solution with minus lambda. So as long as lambda is not equal to 0, these will be orthogonal, because lambda is not equal to minus lambda. So we have our eigenvectors corresponding to different eigenvalues. Those are orthogonal. And so they won't contribute to the trace. Okay? In the trace, we have to take things that are not orthogonal, that are the same. So all that's left is the modes which have lambda equals 0. These are called zero modes. They are things such that the Dirac operator acting on the mode equals to 0. Okay, and because it's equal to 0, it's like it's can be projected on either the left or right-handed part. the left-hand, right-handed parts separately are zero modes. Okay. So we can classify zero modes into right and left-handed parts, and the trace is just counting. Number of left minus number of right. Each mode contributes 1 with the appropriate sign. Okay. So one method of calculating this determinant counts the number of zero energy solutions of this Dirac equation. Now there are technicalities. Actually, you have to look at the Dirac equation in Euclidean space rather than Minkowski space, and you really should put it on a sphere to be completely rigorous. But leaving that aside, the spirit of the thing is that you're counting the number of left minus right-handed particles, or zero modes. So that's one evaluation. Another evaluation is more closely related to the triangle graph, but is done without recourse to perturbation theory. So we want to calculate that functional determinant again. And if you do it naively, you get infinity. So we need to regulate it. And here's a regulation. This is called point splitting regulation. You separate the psi bar and psi. You want to evaluate the trace, so you want to evaluate this with a gamma 5 in the middle. And if you put x equal to y, you have a product of quantum fields at the same point, and that's very singular. To get a finite result, you have to approach this as a limit. And a nice way to do it is to, again, introduce a large mass and a propagation from x to y suppressed by that large mass. Yeah.
I have a question regarding the previous process on the mode expansion, where you simply made some modes with non-zero eigenvalues. But in this case, I'm reminded of the fact that any classical solution to Dirac equation after operation on Dirac operator itself, it is always left with a zero eigenvalue. So is the modes that have a non-zero eigenvalue corresponds to a non-classical solution?
Well, they're all non-classical in a sense because they multiply Grassmann numbers, but it's classical fields times Grassmann numbers. So it's that the modes are classical in that sense, or they're just C number solutions of the Dirac equation, if you like. I'm not sure what you're asking. So there are solutions with zero energy, but there are also 0, 4 energy, whatever you want to call it. But there are also solutions with non-zero eigenvalues. And the result is that the number of left versus right modes is exactly the trace of this determinant we're interested in. All the higher eigenvalues give vanishing contributions to the trace.
Okay, I may have to consider
Okay,
deeper to it.
we can follow up later. Okay, so as I said, this product of quantum fields is very singular. It's basically a delta function of x minus y. When we do the regulator and Fourier transform, we get an expression like this. We put in a k dual to x minus y in doing the Fourier transform. Then we can take the delta function and just have k of x, and we have 1 e to the I kx inside the trace and e to the minus I kx outside, and then this thing in the middle. And by rescaling and allowing this derivative to act on K before we pull it outside there, we get this kind of expression. Okay? So these are mathematical massaging of this original expression to allow it to be evaluated. And now we're going to evaluate it. So that's what we had. And now this expression up here, just spelling it out, we have a term which is the square of that first term. But the first term, remember, is, the first term is the covariant derivative. It's a covariant derivative. So we have, when we, and the gammas don't commute with each other, so we get a commutator of covariant derivatives, which is the field strength, as well as the naive algebraic things you might have expected if everything commuted. Okay. Then we want to insert this exponentiated into the trace with gamma 5. And having in mind that we're going to take the limit of m goes to infinity at the end of the day. So if you're going to take a trace with a gamma 5 matrix and get a non-zero result, you need at least 4 of the ordinary gamma matrices, because gamma 5 commutes with each one separately. Anti-commutes with each one separately. And so if we're going to get 4 gamma matrices here, the only way to do that is to have F appear twice. If F appears twice, it brings down an M, big M to the 4th. So M has to appear, so we need that term, that gamma term, to appear at least twice. But if it appears more than twice, it's dead because we have too many M's in the denominator. So as M goes to infinity, it just goes away. The only contribution is when we use this term twice, expanding the exponential. And that, lo and behold, gives exactly FF dual. Okay? And if you put in the numbers, you'll see that you exactly reproduce the triangle graph calculation that we outlined before. Okay? So there's a lot of algebra to really spell this all out, and some care is needed, but I've shown you all the steps in an honest way. Okay? And so this justifies the historical pure triangle result, which involved some guesswork. And as a bonus, it connects two things that seem totally disconnected, namely the number of zero energy solutions that the Dirac equation has, and the topology of the fields, that is, what the integral of FF dual is, integral of E dot B. It's the integral of E dot B times the numerical coefficient counts the number of left-handed minus right-handed zero modes. Okay, so that's the high point of the hard anomalies. Now, to give some perspective on it, I want to consider a situation that's much, much easier to analyze mathematically, and yet quite important and rich in physics, as you'll see. So I want to discuss the anomalies not in 3+1 dimensions, but in 1+1 dimensions. And in recent years, people have had a lot of fun, and it's been very fruitful to study low-dimensional systems, especially in condensed matter, where 1 plus 1 dimensional systems are also known as wires or edges of two-dimensional materials. And so they're interesting things to investigate. And it's been very fruitful. Okay, so the corresponding phenomena to the triangle anomaly in 3 plus 1 dimensions, in 1 plus 1 dimensions, is not a triangle, but a two-sided surface, as you'll see. So instead of a triangle, we just have a loop with. So we apply similar logic to what you might call a vacuum polarization graph, a simple loop where you have a photon, a virtual fermion loop, and then another photon, another vector particle coming out. But we want to couple an axial current to the vector current. So one has a gamma mu, gamma 5, the other just has gamma mu. By the way, we still use gamma 5 even though we're working in 1 plus 1 dimensions. That's just what physicists do. It's kind of dopey, but that's heavily embedded in the literature. So now we can appeal to Pauli-Villars again. And this time I'll actually kind of show you the calculation, sort of, skipping only much fewer steps. So we have a regulator, just as before, and we want to see if the regulator boson, the Pauli-Villars boson, contributes to the vacuum polarization when we have divergence of the axial current on one side, so that's the gamma 5, and an ordinary photon coupling on the other side, that's the gamma nu here. And then we just have fermion. I'm sorry, not fermion. We have massive spin 1/2 boson propagators elsewhere. Okay. So now we can actually perform the algebra without too much trouble. And we want to see if something survives as m goes to infinity. So it's only going to survive from the high end of this integral here. And so we can drop the p's in the denominator, and we get a result that's indeed finite as m goes to infinity, and takes that particular form. And if you interpret that particular form, that's a p acting on, that's a momentum acting on the polarization index of your photon in an anti-symmetric way, it produces the field strength. Okay, so in this calculation, we've shown that divergence of the axial current here for a massless fermion, properly regulated, contains epsilon AB FAB, which in 1 plus 1 dimensions is nothing but the electric field. There's only one gauge field and has index 0 and 1, and that's the electric field. So it says we have the divergence of this axial current is proportional to the electric field. And with enough work, you could get the actual coefficient. Okay. This has a beautiful intuitive interpretation in 1 plus 1 dimensions. As does this notion of chirality. Okay. In 3 plus 1 dimensions, chirality had to do with the correlation of spin and motion. In 1 plus 1 dimensions, it turns out that it's just motion. All right. So if we take this particular choice of gamma matrices, which you can see they anti-commute and square to 1, so they're fine, and use them to do the projection with the gamma 5, we see that the projectors are 1 plus or minus sigma 3, So the projected spinors are one component objects. And then if you work out the Dirac equation for these one component objects, in other words, functions, you find that it's just d0 plus or minus d1 psi equals 0, which means you have either left propagation or right propagation. That's all. So the projection on left and right-handed particles projects on things that move to the left or move to the right. That's what happens. Left-handed turns into left moving. So our equation can be turned into a relation that says the current that whose zero component is counts the number of right-handed movers and or the density of right-handed movers, and the corresponding left-handed piece, their divergence is proportional to the electric field. And that has a lovely physical interpretation. It says that if you have a background electric field, so the right-hand side is not zero, you will produce chiral charge. You will produce an asymmetry between right and left-handed particles. But we know what an electric field does in the presence with charged particles. You can have a process made famous by Schwinger, where if you have an electric field, it becomes energetically advantageous to produce fermions, to produce these charged fermions. And then if you do it right, the electric field that connects them, the electric flux that connects them will cancel part of your electric field and you can gain energy. And if they start far enough apart, you'll gain enough energy to have the rest mass that they had, and you'll produce those fermions. So there's a clear physical process that discharging of electric fields by spontaneous production of pairs that fulfills this equation. Okay. By the way, in 3+1 dimensions, there's also a physical interpretation, but it requires quite a bit of more work, because in the three-dimensional case, it's E dot B. What you have to do is set up parallel electric and magnetic fields, analyze the particles in the presence of a magnetic field. You have Landau levels, and then you get a similar process involving those flat bands. Okay. Now, if you remember, left-handed was left moving and right-handed was right moving. So if we produce a pair, we have a left-handed and a right-handed of opposite charge, though, of opposite electric charge. So one is a particle, one is an antiparticle. That means we've changed the number of left-handed particles minus right-handed particles by 2, not 0, 2. We've violated the axial conservation law. So that's what the anomaly is. You spoil the conservation law when you take into account this quantum mechanical process, or sort of a tunneling process of spontaneous pair creation. So it's all this mathematical hocus pocus reflects something that really should exist in the physical world and is an inevitable consequence of applying quantum mechanics to this kind of theory. And we notice with amazement that although our basic interaction of gauge fields with fermions doesn't change their chirality, it connects only left to left and right to right, this process does create 2 units of chiral charge. So this non-perturbative process it violates the symmetry of the classical theory. Okay. So That's the interpretation of the anomaly equation. It means that, as in QCD, when we introduce a theta term that has no classical significance, it has significance in the quantum theory, here, the corresponding theta term, instead of E dot B, will be just E. Instead of epsilon FF dual, epsilon FF, it's just epsilon F. All right? And it has zero divergence. I mean, it's a total derivative. It's the field strength, so it's directly a total divergence, and it has a simple. So what is the theta term? Well, the theta term is nothing but an electric field, and so adding that to a Lagrangian is just adding a background electric field. In other words, it's adding a capacitor. If we put a negative charge on one side and a positive charge on the other side at infinity, we get exactly this kind of background electric field. That's something that the world might produce. If you're looking at processes within a finite region, you have to impose some hypothesis about the boundary conditions at infinity. And one thing you might posit is that there's an electric field. However, there's one subtlety that is very pretty and has to be mentioned here, which is, remember, in 4 dimensions, we argued that theta was periodic, that if you changed it by 2 pi, you'd get the same theory. Same thing here, because if the field is something that can be decreased by producing a pair and letting them go to infinity, that will happen. Okay? It won't be a stable state. If you want to describe the stable states, you can only, remember, this is 1 plus 1 dimension. So Gauss's law tells you have a flux from a charge that just keeps going. It's constant. If you have an electric field that's small enough, you can't gain energy by producing a pair and decreasing it. And that gives you a periodicity. If it's large enough, you bring it down into that region where it's very small. So that's what happens here. So the theta term is a background field. It's a dimensionless parameter that measures it. And if we combine the Maxwell Lagrangian with this new theta term, it looks like this. And the effect of theta is to encourage a background electric field. Okay. I'll show you one more application of this idea to a state of matter that's caused a lot of excitement and 3 or 4 Nobel Prizes in physics in the past 4 decades, I guess now. That's the quantum Hall effect. And we're going to make it simple. We're going to show why the quantum Hall effect is an elementary application of the anomaly. With a few assumptions. All right. So we're going to connect them. I wouldn't say this is a derivation in any sense, but it's a connection between the anomaly and the quantum Hall effect, which shows one of the main characteristics of the quantum Hall effect, namely that if you have the quantum Hall effect in a finite system, there necessarily are massless modes that flow around the edge of the theory. So you start with a lump of material in a background magnetic field, and you discover that at the edge of this material, when you're in this kind of state, there are massless excitations, so very low energy excitations, which or describe an edge, excitations along the edge of your material. Okay, so the essence of the quantum Hall fluid is that you have, in the presence of, this is in 2+1 dimensions, and in the presence of a magnetic field, you have a current perpendicular to it. That's the Hall effect. Okay, and the quantum Hall effect says this occurs with a quantized coefficient in the right circumstances. So the quantum Hall effect, this flow, can be described using an effective Lagrangian density that looks like that. If you take the equations of motion for this so-called Chern-Simons term, you get exactly this kind of Hall relationship. So the derivative with respect to A is the current, and that's the current you get. Okay, so that's fine. But now let's this term that gives this, that generates the equation of motion, is a little bit funny. Usually we say that A couples to a conserved current. So there's some kind of current here, but this is a current, a very unusual current. It's the field itself. And so we have to be careful that we haven't spoiled gauge invariance. That would be something that shouldn't happen, because the underlying theory is gauge invariant. It shouldn't be, and it would be catastrophic in many ways. We don't want that. So if we but on the other hand, we want to apply this effective description to a finite sample. Okay. So let's check the gauge invariance of that theory in a finite sample. So we have this action, this action, applying only in a finite region of space, which I'll call gamma. And now let's make the gauge transformation. And it sort of works, okay? Because after all, epsilon f does automatically have zero divergence. So if we don't worry about surface terms, it's fine. But if we want to apply this inside a finite region, because empty space doesn't have the quantum Hall effect, then we have to worry about that surface term. So we have a theory that's not gauge invariant because there are nasty surface terms arising when we do the integration by parts. But we know a clever way to generate theories that are local, that obey general principles, and violate gauge invariance in a very structured way. In fact, exactly the way that this is happening. In 1+1 dimensions, which is the boundary of the 2+1 dimensions, we can have a theory with massless fermions that has a chirality, so we have right or minus left, not zero, and then we'll have an anomaly, according to the discussion we just had, and that anomaly can be quantitatively something that exactly cancels the bad gauge transformation property of the effective theory in the bulk. So the anomaly of the surface theory, instead of a defect, becomes a virtue when it cancels the anomaly, the surface anomaly of the bulk, and makes the whole theory consistent. So to make the theory consistent with gauge invariance, we can have that funny Chern-Simons term in a finite region, but we must have an anomalous theory on the surface. And we know how to produce that anomalous theory. So this is a simple but sophisticated way to understand the emergence of unidirectional edge currents in the quantum Hall effect. And that's a logical place for us to stop. So, and we'll pick up this discussion next time and apply it to QCD. Remember, let me remind you of what we're doing here, the big picture. There'll be a spoon appearing. And we better, let's. Okay. We're going to have in QCD a symmetry which is of the classical theory, which is not a symmetry of the world, but then we'll find that there's an anomaly that makes that okay. But that same anomaly also means this theta term, which violates time reversal symmetry, is physical. Okay. You can't have one without the other. They come together. And that will upset our understanding of time reversal symmetry and set up what's called the strong P&T problem. Okay. So that's the program we're trying to carry out. And then we'll solve the strong P&T problem, but at the cost of introducing an expansion of the standard model to include axions, and then axions will turn out to be a wonderful thing that is probably the dark matter of the universe and is a great target for experimental work in coming years. All right, so then we'll have many interesting byways as we do that, but that's the program for probably the next lecture. Okay.
All right, so any questions from the audience? Okay, any questions from audience? Students?
Yeah, here's one.
Hi, Professor. Can you turn to the page 53? So,
53.
actually, yeah. So in this, here you consider the triangle Feynman diagram.
No, this was not the triangle. This was the loop. This is 1 + 1 dimension.
Yeah, 1 + 1. But
Yeah.
the process you consider is not it's just a fermion and coupled to boson.
To 1 photon.
To 1 photon.
In 3 + 1 dimensions,
Uh-huh.
we're coupling to 2 photons.
Oh.
Here in 1 + 1 dimensions is just 1 photon. So the anomaly is just an electric, the right-hand side of the anomaly is just an electric field.
So why it could be a how to say background potential, not the decay process or such the pair. So why first of all why is coupled to one? Okay, why is if coupled to 1 photon is the energy conserved? Is that you mean this photon is not the
Well, it's the photon can represent a constant electric field.
For
instance.
I get it. So
Yeah.
so there is an actual field we put on
The divergence of this current is equal to the electric field density. That electric field density can be anything. Whatever it is, that's the divergence of the current. That's what the equation says.
Okay, I got it. Thank you. Oh.
Okay.
Okay, more questions?
Yes, I want to continue to ask his question. Is that, but now doesn't that mean we can have arbitrarily many photon external lines?
We could have more. We could have more external lines too.
Yeah, but how to determine the leading order contribution to this possible anomaly? Because in
in 3+1 dimensions,
yes,
I showed by this non-perturbative calculation with the regulator that the only contribution is the triangle graph. If you do something similar in 1+1 dimensions, you will find the only contribution to violation of the chiral symmetry is coming from this loop graph.
Okay, I see your point.
All the other graphs will be basically because they have more powers of virtual momentum in the denominator, they will be better behaved and the regulator will go away without leaving a trace. It's only in these small trace in the, that's not, pun not
okay.
intended,
I
without
think
leaving
you're
any
right.
relic. It's only a very small number of graphs that are sensitive to the need to regulate and give you a finite answer after careful treatment that you didn't have before and violate the symmetry. So from the point of view of Feynman graphs, it's not completely obvious that these are the only contributions, but you can show it non-perturbatively. And so, there's certainly interest in calculating more complex Feynman graphs, and you get all kinds of things can happen. But if you're focused on violation of this symmetry, it's just those graphs that give all of it.
Okay, I see. But is it a simple method to demonstrate that the case is indeed as you just have described?
Well, if you consider that calculation using point splitting simple, then it's simple. But
Thanks.
to make it rigorous, okay, so it's simple once you understand what path integrals in function space are and Grassmann variables. And so once you reach a certain level of sophistication, it's very simple. But you have to get to that level.
Okay, I see.
All right.
Thank you.
Okay.
All right. Any more questions? So maybe I can ask a question.
Yes.
There's also a student.
Okay.
Students first.
Okay, Professor, I have a question about the last parts about the 1+1 anomalies.
Yes.
You give us a very, very sophisticated picture about how the Lagrangians show the bound effects.
Yes.
And I want to ask, that picture could give us some idea about the edge states.
Yes. Well, this shows and it shows that the edge states really represent very low frequency modes, that they have to be there, and that they propagate in one dimension. So it has all the main qualitative features of the edge states are coming out of this way of maintaining gauge invariance.
I see. Do you mean that the contribution of the edge states will result in they will contribute to the anomalies, and they will?
Yes, they are. So
okay.
Again, the edge theory
Yeah.
has this anomaly. So it has an epsilon F, where the F is the current, is the field in the direction of the edge. And it's exactly what you get by integrating that effective bulk interaction, that Chern-Simons term, by seeing how much it violates gauge invariance. So the gauge invariance of the bulk theory at the edge is canceled by the anomaly of the edge theory at the edge. And That's how it goes.
I see. Thank you.
So if you like, there's a modified gauge symmetry, which acts in the usual way in the bulk, but also is a chiral transformation on the edge. So there's a.
I see. Thank you.
Okay, more questions? Feng?
So, in the integration, you want to remove this infinity, then you introduce a particle with the spin 1/2, but you still call it as a boson.
Yes.
Is it because it has to satisfy this boson statistics?
Well,
Why-
it's
why
because
they
you
call it
want
a
it.
fermi?
It's because you want it to occur in the loop, to contribute to the loop with the opposite sign.
Okay.
Don't
so-
blame me. It's Pauli and Villars. Yeah. No, it's a very clever proposal, and it does the job. Okay, but it's a mathematical device. This particle doesn't exist. It's very, because it would violate principles of quantum theory. If the spin statistics theorem is based on some very significant principles. You don't really want to violate it, but that's why you need to take the mass infinity all the way to infinity, which means you can never produce this particle, and so nothing is violated. It's like the Cheshire cat, just the smile was left behind. The cat is
Right. It's like in field theory, people want to calculate something, then it diverges, and they usually imagine another thing that also give a minus divergence, and that's cancel out
yeah.
give
Well, it sounds more dubious than it is, I think. But it's very profound. The profound way to think about it is that to define, the only way we really know how to define quantum field theories rigorously is by a limiting procedure. We first put in a cutoff, and different kinds of cutoffs are used in different contexts. Pauli-Villars is very nice for perturbation theory. There's something called dimensional regularization, which is also very popular in perturbation theory. And then you put a more powerful way that doesn't involve perturbation theory is to put the theory, to discretize the theory, put it on a lattice, and that's what's used in lattice QCD. You define the theory fully non-perturbatively, but in the case of the lattice, you want to take the lattice size to 0 so that you can have the rotation symmetry and translation symmetry that you want in the final theory. And in these other techniques, you take the Pauli-Villars masses to infinity so that they're not left in the physical spectrum, or in dimensional regularization, you work out the theory in dimensions 4 minus epsilon, close to 4, or 2 minus epsilon if you're doing, but then you take epsilon to 0 after using it as a regulator of the infinite expression. So that's how the theory is constructed. And it sounds bizarre, but it's the underlying physical phenomenon is that quantum fluctuations of very high energy and short wavelength, at short distances, are real, and it's the residue of the black body catastrophe, if you like. We still have these quantum fluctuations at very high frequency, and they have important effects. The anomaly solves problems. It's not just a problem. So you really want that to be in there. The asymptotic freedom really does describe experiments, so you really want that. Vacuum polarization in atomic physics, the Lamb shift, all those things are real. So, and they reflect the fact that these fluctuations are for real, and so you have to live with them. You have to deal with them honestly. Yeah.
Right. The quantum fluctuation is a really real thing. It can give all kinds of phenomena, from the Lamb shift to the spontaneous decaying of atoms, and also to the Casimir effect.
Right.
So
yeah, that's right. So Casimir effect is another good one. So so God has spoken. This is what you have to do.
Right. And Frank, maybe I can ask the last question.
Yes.
So in this lecture, you mentioned you teach us about this 3+1 dimensional quantum anomaly,
Yeah.
and also 1+1 quantum anomalies. So I know that but there's no 2+1 quantum anomalies. So it's kind of quantum anomalies are always generated by quantum fluctuations. Seems 2+1 dimension. It's kind of quantum fluctuations can notice.
In 2+1 dimensions, there's not an anomaly in the sense that you have some chiral current that's that would be conserved and is not, because basically the right-hand side has to have epsilons and f's, and there's nothing you can do in 2+1 dimensions.
Right.
But there are related phenomena. So there's a what's called a parity anomaly.
Oh, parity anomaly.
There are related phenomena also in 2+1 dimensions. So the deep structure of quantum field theory still shows up in 2 dimensions, but in slightly different ways.
I see. So 2+1 dimension seems really special.
Yeah.
Okay.
Well, it's really 2+1 is special in the sense that, well, you can have low dimension operators which are on the verge of not being gauge invariant, but are these Chern-Simons terms, and they show up in the quantum Hall effect. They show up in anyons. They show up in all kinds of interesting ways that have been focus of a lot of attention recently.
Okay.
And they're closely related to the anomaly. Like the anomaly, they tend to violate discrete symmetries like time reversal or charge conjugation or parity in different cases. And like the anomaly, they are connected to the divergence structure of the theory. They can arise that way. Yeah.
Okay, the last question.
Yes.
Thank you very much. So this is a naive question. You mentioned that in the 1+1, you will produce these 2 particles.
Yes.
So people are trying to use very high powerful lasers to generate a very high density of electric field, and this will produce these 2 particles. But my question is, you mentioned that in the case the 3+1, you will need electric field plus a magnetic field.
Parallel electric and magnetic fields.
So my question is, what kind of particles you will produce, and what will be the quantities to measure to verify that you have produced?
Well, it's the same thing. You'd produce pairs that would be moving in funny ways. I don't know offhand. We could figure it out.
So, but you need the second photon.
You have E and B. I think they would move in the direction of the E and B fields in opposite ways.
So you need the magnetic field.
You need both. Yeah, you need E dot B, right? That's what appears in the anomaly equation. So it's more complicated, but very similar in spirit.
Yeah,
Let me just add, in the case of 1+1 dimensions, although if you want to do this in vacuum, you need very strong electric fields, and it's not easy to do because you need very high vacuum as well as strong electric fields, because if any kind of matter is around, you can ionize the atoms, and that's generally easier to do than producing electron-positron pairs. But in solids, you can have electrons in holes, which are much lower in energy, and you can produce electron-hole pairs according to this mechanism. And in fact, that's the way that Schottky diodes work. So it's actually the basis of very tangible devices in condensed matter physics. And long before Schwinger, this process was analyzed in that context, condensed matter physics, by somebody whose name escapes me at the moment, but they deserve a lot of credit for doing it. It's really very much the same thing, just not in vacuum, in materials.
Right. In materials, a lot of things can become easier. Like in 3+1 dimension, like there's solid, so-called Wilson metals. If you apply a parallel electric and magnetic field, you will get a carrier current in the solids. That's something studied a lot recently.
Yeah, so it's exactly getting the E dot B. And the point is that in solids, and especially in wild semimetals, where you have, in effect, relativistic dispersion relations for the electrons and holes, the holes are cheap, much cheaper than positrons.
Right.
And so these effects are much more accessible. Yeah.
Okay, thank you. We have a very sophisticated, but a very also beautiful and simple lectures today. So let's thank Frank again.
Okay, thank you. Yes.
That's maybe too naive question.
All right.
It doesn't miscast 2 points.
Okay, I have to do an intro.